Hey guys, welcome to Unit 13, Note C. Today we're going to talk about half-life. So, all radioactive atoms decay. What does being radioactive mean? It means that you have the wrong proton and neutron ratio. So, some things will decay faster than others. They all have different rates because they would all have different stabilities. It's all about that ratio. So, when I'm talking about something that is unstable, I can actually call that a radionuclide. Remember, nuclei just means an isotope. So this would be a radioactive isotope, which would decay at different rates. So here's our equation to determine the rate of decay for a given element, or given radionuclide, I should say. So the logarithm of the original amount, which I'll call A naught, over the amount that you end up with after some amount of time. So the lowercase t over here being time. K is going to be a rate constant, very similar to the rate constants that we looked at in Unit 10. We're going to actually look at another formula to determine that rate constant based on the half-life. And we'll be able to use these two equations together. So this is a logarithmic ratio of the amounts compared to a constant as a multiplier of time over 2.303. If I don't actually know the amount, I can use a variation of this formula where I'm looking basically at the numbers, or n naught over n. We're also going to look at a question like this in the notes, where I'm comparing something decaying at a certain rate, maybe 60% as fast, has 60% as much of the product left in it. So whenever I don't actually know the amount, I am technically using n as opposed to a, but it works exactly the same, and I tend to treat them exactly the same. I even say, like, let's make up this amount instead of using an n. So we'll take a look at that in just a minute too. Half-life is an exponential decay. So a graph of half-life would look something like this. Half-life is defined as the amount of time for half of a substance to decay. So where I start with 100 grams, after one half-life, I would be down to 50 grams. After a second half-life, that 50 grams would decay to half of it at 25 grams. So in my first half-life, I'd be losing 50 grams, whereas in my second half-life, I'd only be losing 25 grams. So starting at 25 grams, for my third half-life, I would lose half of that, or 12.5 grams. So notice that as you go into further and further half-lives, there's less and less to take half of, which is going to kind of flatten out that curve. So it starts off with a steep drop, and then slowly kind of levels off. We call this exponential decay. But half of something is always something, right? Half of something can't be nothing. So we're never actually going to hit the zero here. Think of it as a limit. You're always going to have some radioactive substance left, and that is the nature of half-life. That's part of why radiation is so dangerous. If we look at this as a form of concentration of reactant kind of breaking down, this would be our parent cell producing some other substance. The product of decay would be our daughter cell here. So this should remind you a little bit of reactants decreasing and products increasing when we did study Unit 10. So there's a lot of relationship here between how the rate works and the rate of decay works. So how do we apply the half-life to determine a rate constant? So the rate constant is equal to 0.693 over the half-life. And this is the version of the equation that we'll typically be using in our formulas because we're going to be looking for k to use in that other equation. And here's where it comes life. Half-life is a function of 0.963 coming from the natural log of 2 divided by k. So you can tell mathematically these k and t1/2 are kind of interchangeable. So it's also possible if you're given the k, or if you use the other equation to get k, we could use that to then solve for the half-life. So either way, this is our second version of the formula. All right, let's try putting these formulas to use. So I have cobalt decaying, emitting beta particles and gamma rays, and here I see my half-life. So whenever I'm given half-life, I know I can find k. So I'm going to use the t1/2 equal to 5.27 years. So k is equal to 0.693 divided by the half-life of 5.27, oops, I don't know what I was reading there, 2.7 years. So this is a fairly simple division, but watch your units. That top number doesn't have any units, where the bottom number has the units of years. So when you do your division, we get 0.131 inverse years, or years to the -1. This is important as I look at my second formula because I want my rate constant k, inverse years, to cancel with the time for t, which is going to be regular years. And top and bottom will cancel out there. So now let's look at the rest of the question so we can move on to our second formula. The question says, how much of a 3.42 microgram sample? So is that 3.42 regular A or A naught? A naught is our original amount, that starting point. So if I'm asked how much is left, I probably started with the 3.42. So that's my original amount in micrograms. So that means I must be solving for the amount that's left. I have one more variable here. This 30 years would be the actual time. So the half-life is 5.27 years, meaning for every 5.27 years, half of the cobalt decays. The question is, if I'm at exactly 30 years, how much is left? So we've kind of got to factor in the half-life's role over the 30 years, which is where the K comes in. Now let's start plugging in. We can plug in the 3.42 on the top. We're going to be solving for A, which is going to be tricky because now we have X in the denominator inside a logarithm, which is going to be kind of a lot to unravel. We'll be able to plug in the K value and our T of 30 years. So let's go ahead and plug those guys in. The first thing that I would recommend doing, since this is a lot to unravel, is to go ahead and squash this. Go ahead and get that part in the calculator. Inverse year will cancel with years. That's kind of what we were talking about up here. Be careful with the units. And so you're just going to be doing the 0.131 times the 30 divided by that constant 2.303. And we should get 1.71. The units are all gone. This is my simplified version of the equation right now. Now I need to solve for A. How is this going to work? The first thing that we need to unravel is the logarithm. Then we'll have to deal with X being in the denominator. So the opposite of the logarithm was our antilog. So I need to antilog both sides, meaning I need to raise 10 to the power of 1.71. Almost. There we go. So how to solve for A? First, logarithm. Get that out of there by taking the analog of both sides. So taking the analog of a log, of course, completely undoes it. That was our point. Now I just need to find the antilog of 1.71, or basically I need to find 10 raised to the power of 1.71. And so that is 51. The next problem is that X is in the bottom, or A is in the bottom. So in order to get that out of the bottom, I'm going to multiply both sides by A. So I end up with 51 times A, and setting that equal to the 3.42. So now to isolate A, I'm dividing by 51, and I finally get my amount of 0.066 micrograms. Notice the only unit still left here is the micrograms and how that appears in the final answer. And doesn't it make sense that the units for the amounts would be the same? By the way, also your units for the time and the half-life should also be the same. So one quick comment here on Sigfigs. When we were finding the antilog of 1.71, that's kind of like antilogging a pH. And remember, the decimals of the pH became the significant figures of my answer. So because I have 0.71 two decimal places, I get two significant figures for the 51. So that's where my Sigfigs are coming from, was those Sigfig rules with logarithms. All right, so that was a big question. Now let's look at some applications for using this half-life. One big one is something called carbon dating. So you may think of carbon as a fairly neutral molecule. Carbon 12 actually would be the 12-6 for carbon off the periodic table. But there's actually a very common isotope called carbon 14, which is radioactive. Carbon 14 would have two more neutrons than carbon 12, meaning it has the wrong proton-neutron ratio, making it radioactive. So it's going to spontaneously decay because it's radioactive. It's constantly replenished in things that are alive due to the carbon cycle. But once something dies, then it's going to start to decay, and it's not going to be intaking more carbon-14. So we can then look at the rate of decay as a function of how much carbon-14 is still there. So this is one of those examples where it doesn't give you the amount. So we have to think through this practically, and technically the version of the formula that we'd be using is the one with the N instead of the A. But you'll see that's not that big of a deal. So I see this very wordy problem that has two important numbers in it. My 0.636 is telling me how much more reactive something is. And then my 5,730 years, it says, is the half-life. Well, let's start with what we know. If I'm given the half-life, T1/2 of 5,730 years, then I can find K, which is going to be 0.693 divided by that half-life. Again, watch the units. We can get K by doing this simple division. 0.693 divided by the half-life, and we get a K, let's just use it from here, 0.000121 inverse years. Now that I have K, I can start thinking about my other formula. So it was the log of A0 over A equals KT over 2.303. And now technically, because it doesn't have amounts, I probably should have written N here, but it really doesn't matter. What I need to know is how much amount I have left compared to how much I started with. And that's what this rate here tells me. If I read this carefully, it says we find this piece of wood, and wood, of course, would come from a dead tree, right? So the tree was alive, and when the tree is alive, it has 100% of the carbon-14 it's supposed to. Once that tree dies, this decaying piece of wood is found to have 0.636 times that amount of carbon-14, meaning it has basically 63.6% of the carbon-14 that a live tree would have. So we've made an assumption before for original amounts or total amounts. What if I said I had 100 grams? If I started off with 100 grams, and then later on I had 63.6% of that, later on that amount would be 63.6 grams. Notice how the grams would cancel, so you could make up 100 kilograms, 100 micrograms, it really doesn't matter because the units cancel. So I just want to make sure that my bottom number is 63.6% of my top number, because it should be 0.636 times the top number. Now I'm going to be able to plug in my K over here of this 0.000121 inverse years and solve for the time. How long has this decay been occurring based on this ratio? So now it's time for calculator. So notice how they're using the NO, same thing. I'm making up that I have 100 to start with, and I end up with 63.6 later. So first thing you want to do is your 100 divided by your percentage. So that's going to be 1.57. Then when I find the log of that number, I can divide it by the K, and that'll isolate my T. So the log of 1.56 would be 0.197. So notice these significant figures became my decimals, 3 sig figs, 3 decimals. And then when you divide that by your K value, you get the time that must have passed. Very long time, 3,730 years. So what's tricky about these ones is using that percentage correctly. Whenever you're working with percentages and you need a starting point, go with 100 grams. All right, so carbon dating does have its limits. If an object is really old, we would have to use something that has a longer half-life. So generally the cutoff is around 50,000 years for carbon dating to still work efficiently. Once that time kind of passes, the amount or percentage of the carbon that's left in order to use for dating, like in the last example, would just be too small for us to actually use. So there are a couple workarounds. The first would be the potassium decaying into argon, which has a half-life of 1.3 times 10 to the 9th years. And then a bigger one would be uranium decaying into lead, which takes 4.51 times 10 to the 9th years. This really long half-life of uranium, by the way, is also why it's a good choice for fuel for nuclear energy, because it takes a really long time for half of it to decay. So that, combined with its efficiency, makes it a good choice for the nuclear energy. It also can be used to determine the ratio of uranium compared to lead in order to determine how old older substances are. So that's going to do it for carbon dating and radiotide dating in general, and that's our half-life notes. So that's going to tie up everything in Unit 13, and our next and last unit will be Unit 14, where we're going to study organic chemistry, my favorite. We'll see you there.